All right, today we're going to dive into the data structure that powers some of the absolute fastest features you use every single day. We're talking about tries, which you'll also hear called prefix trees. And trust me, they are the secret sauce behind that super fast autocomplete we all know and love. You know the feeling, right? You start typing AP, and before you can even think, your phone is suggesting Apple or application. It seriously feels like magic. But it's not magic, it's just a really, really clever data structure doing its job. By the time we're done here, you'll know exactly how it works. And the solution to that whole instant suggestion puzzle? It's the tree. That's spelled T-R-I-E, but, and this is important, it's pronounced tree, just like the one in your backyard. And it's built for one thing, handling strings and their common starting letters, or what we call prefixes. Honestly, the best way to picture a trie is as a roadmap, but for letters. Every turn you take is a different letter. Now, instead of storing whole words like apple and application in two completely separate boxes, a trie shares the path. That shared journey is the secret to its incredible speed and elegance. So how do we actually go about building one of these letter roadmaps? Let's just walk through it step by step. The whole idea, the core concept, is to share the path for as long as the words have letters in common. Everything starts with a single empty root node. Think of it as our starting point. Now, let's say we want to insert the word app. We simply create a new path, a branch for A, which then leads to a branch for P, which finally leads to one more P. And here's the most important part. We have to mark that final P node with a special flag that says, hey, a complete word ends right here. Okay, now let's add the word apple. And this is where the magic happens. We start by tracing the path for app. But wait, that path already exists, so we don't create anything new. We just travel down that existing APP path. From there, we just add on, branching off with new nodes for L and then E. And of course, we mark that E to show it's the end of another word. You see? That right there is the core efficiency of a trie. Common prefixes get stored only once.
Okay, so we've got our structure built. Now how do we actually use it? Well, understanding the main operations, like checking if a word exists versus checking if a prefix exists, is really the key to unlocking all of its power.
Now, you really want to pay attention to this slide because this distinction is everything. If we ask our trie, do you contain the word app, we walk the path A, P, P. When we get to the end, we ask one more question. Is this node marked as the end of a word? In this case, yes, it is. So the answer is true. But what if we ask, does any word start with app? Well, then all we have to do is find that path. We don't care about the marker at all. As long as the path exists, the answer is true. And just like that, we're right back where we started. Autocomplete is nothing more than a starts with search followed by a little bit of exploration. When you type AP, the system zips down the tree to the node for that prefix. Then it just looks at all the possible paths that continue from that point, finding app, apple, and maybe apricot, and shows them to you as suggestions. It's that simple. Now, autocomplete is cool, for sure. But what if I told you we can take this concept and build something even more powerful? Tries aren't just for simple lookups. They are incredible for optimizing really complex search problems, like finding all the words on a boggleboard. I love this quote from our source material because it just nails the idea. Imagine you're scanning a grid of letters. As you're building a potential word, say OAT, you're constantly checking the trie. Is oat a valid prefix for any word in our dictionary? Yep, for oath. Awesome, keep going. But what if you try a path like OAX? You check the trie and nope, no path for OX exists. The trie acts like a guardrail, telling you to stop, turn around, and go back immediately. This ability to just prune away all of the bad branches from our search tree is an absolute game changer. I mean, instead of blindly trying out every single possible combination of letters, which would be astronomically slow, the trie lets us know we're on a dead-end path instantly. This is what makes solving a big, complex word search even possible on a computer. So, we know it's fast. But how fast exactly? And is there a catch? Let's get into the nitty-gritty of performance, which, by the way, is exactly the kind of stuff you'd get asked about in a technical interview. Now, what's so cool about this slide is the time complexity. Look at that. Everything is OL, where L is just the length of the word you're searching for. Notice what it's not dependent on, the total number of words in your dictionary. Whether you have 10 words or 10 million, finding apple takes the same number of steps, one for each letter. That's incredible.
If you remember one single thing about how fast a try is, let it be this: OL. The time it takes to do anything is directly proportional to the length of the string you give it. That's it. It's unbelievably predictable and ridiculously fast for short queries.
All right, let's bust a couple of common myths real quick. First, people often assume tries are always super space efficient. Well, they can be, but a simple implementation can actually use up a ton of memory for all those pointers, sometimes even more than a hash table if you don't have many shared prefixes. And second, the search is not O of run, or constant time. It's O of L, which is amazing, but it's important to get that detail right. Okay, let's zoom out for a second and just wrap up what makes this try data structure so important and so incredibly useful. So let's boil it all down. At its heart, a tree's power comes from one beautiful, simple idea: sharing prefixes. That's what gives us that blazing fast O of N performance and makes it the perfect tool for things like autocomplete. But don't forget its other superpower, acting as that guardrail to just slash the time it takes to solve much, much bigger search problems. Look, the theory is really powerful, but the real, deep understanding, that comes from actually building one yourself. You've got all the core concepts now, the nodes, the child pointers, and that all-important end-of-word flag. So the only real question left is, what are you going to build with it?